Hello, this is Brent Ritchie, and I want to talk with you a little bit about domain and range and in general, and then specifically how it pertains to functions and their graphs. So let me get started here. Functions are often defined in not functions, domain and range are often defined in very general terms related to functions. Sometimes you see them as these little blobs. And we'd say, okay, this is a domain group here over on this side, and here is a, just write a little more legibly, domain. All right, there's my domain group. And this is my range. And there's some function that takes elements from the domain and matches them up with elements in the range. Now, these elements can be anything in a math sense. If you become a math major one day, you'll do this with all kinds of things besides numbers. But functionally, for algebra purposes, we deal with numbers. So I'm just going to look at it with numbers here, and I'm going to use the function notation we use in algebra as well. So I'm going to say that this matching is done with some function f of x. And I'll show you an example because sometimes it's easier to understand with an example than it is a definition. And maybe we have some elements in this domain, 1, 3, 5, and 7. And maybe we have stuff over here that 2, 3, 5, and 10 in the range. And this function f says that 1 gets matched up with 2, 3 gets matched up with 10, 7 gets matched up with 3, and 5 gets matched up with 5. So that's a pairing of these four numbers in the domain, 1, 3, 5, and 7, to this set of numbers in the range 2, 3, 5, and 7. So that's sometimes how you see domain and range written. Now, in algebra, in general, the domain are typically our x values. Those are the numbers that we plug into a function. What comes out, which is your y values, that's your range. It's either a y or sometimes we use the f of x. Often you will see it written, well, not often, but this is one way to represent a domain and a range in a function. And another way to write this same relationship, you'll see them as ordered pairs, just like the ones that you plot on a Cartesian plane. And we'll say, okay, this is 1, and that is matched with, and we know that from up here, we look up here to see 1 goes over to 2. So we would write that as an ordered pair, 1 and 2 paired together. That means this one is matched with, in the domain, the 1 in the domain is matched with the 2 in the range. And then we look up here and our 3 is matched with what? Down here, 10. So we'd say the 3 is matched with 10. And you can also look at these as x's and y's if you want to. The value 3 is an x, and when you plug that into your equation, into your function, 10 comes spitting out. The 5 goes to the 5. And finally, the 3 goes to the 10. These x values, these first values here, these are the numbers, the elements that were in the domain of this function. Those are the domain values, and the values that they were matched with, the y values, the f of x values, those are our range values. So typically in algebra, your domain is nearly all the real numbers are almost all the real numbers. In some cases, it's not. You know, when you do with square roots and things like that. And sometimes when you have rational functions where you have to worry about zero in the denominator, you don't have a domain that covers all the real numbers, but a lot of times you do. I'd say most of the time, especially with polynomials and things we're used to playing with. And of course, the range differs depending on the function that we're dealing with. But it's whatever comes out. When we take all those numbers that we decide are in the domain and we put them in those functions and we get all these numbers back out, whatever we get back out, that's the range. Sometimes it's all the real numbers, sometimes it's not. Oftentimes it's not. And sometimes it's easier to see all this on a graph. But this is just looking at domain and range from a function standpoint. You've probably already talked about functions and the restrictions on functions. You know, one of those restrictions on functions is, let's see, I have these two sets here. If I have a number 1 over here, and I have a couple of elements over here, say a 2 and a 5, that this one cannot be matched with two different numbers in the range. So you can't plug in one X value and get two Y values back out. If you do that, if that happens, then it's not a function anymore. It's not a function. So we limited ourselves right now to just functions, and functions has significant value in math and in applications and things, and that's why we talk about them separately. But this is one of the big properties of functions. This cannot happen here. We don't like that. Now the opposite of that can happen. This is what makes it a little bit confusing. Suppose you have two numbers over here in the domain, and I guess I should be careful to label these. That's my domain blob, and this is my range blob. Now this is possible. This can happen. You could have two values in the domain go to the same value in the range, but not the other way around. So two values, two different x's could go to the same value of y, and still you could still have a function that way. But you can't have one x go to two different y's. So an easy example of that is when you think of a function like this, f of x equal to x squared. If you plug a 2 into that function, you get 4 back out. If you plug a negative 2 in that function, you get a 4 back out. So in this case, the negative 2, I want to draw it using my blobs, these things. And I'll get away from the blobs soon enough, and we'll talk about it just with equations. It would look like this. The negative 2 in the domain, that in the function is f of x equal to x squared. Well, negative 2 squared is positive 4, so it goes to that. Positive 2 squared is also 4. So under that function, two different numbers in the domain get matched to one value in the range. Perfectly legitimate thing to happen. What you can't have happen is one value in the domain going to two values in the range. We like functions because they're predictable. When we plug one number in, we always get one number back out. We don't want to get two numbers back out because then they become a little unpredictable and they wouldn't have a whole lot of value, now would they? We can look at this, the implications as far as graphing goes for domain and range. Let's see. Find my calculator here. There we go. All right, so here's my calculator. Let's look at some functions, the graphs of some functions, and then kind of see from a graphing standpoint what the domain and range look like. I'll use the same function notation just because I want to be consistent. So I'll use this f of x notation, even though it takes a little bit longer to type in. F of x equal to, let's do that x squared, which of course is the same as writing y equals to x squared. It's just a matter of notation. Let me move this down here where I can see it a little better. All right, so we can see from here that these x values, these values along the x-axis, say 2. Now let's pick a different one. Let's pick 3. Here's 3. That's the value of x, and that's the domain. These are our domain values. These are the values we plug into the function. And when we plug the 3 into the function, we come up here to our graph and over to see which y corresponds with it. And we see that y up here in the range is 9. So the 3 pairs with the 9. The 3 is in the domain. That's our x value. And the 9 is the corresponding value in the range. That's our y value. And we could continue this. And you can see that from the graph, we can pick any number along this domain. And if we go up high enough, we're going to eventually hit that graph, and we can come over to the y-axis and find a y value associated with that. I know it kind of runs off the screen here, but you could, even if you said, well, what about when x is 10? Well, that's 10 squared, because this value, this function is f of x equal to x squared. So that's 100. So 10 gets matched with 100. That's way off the top of my screen, but it's there. What you don't see is this graph extending to the negative y-axis at all. There's nothing down here below the x-axis. There's nothing down here on the negative y-axis. That means our range for this particular function, our range is only the y values that are greater than or equal to 0. All these that are up here, because down here, there's nothing. There's nothing down here. This graph never extends below the x-axis. So all these y values that are taken on are on the positive y-axis. Now the domain, on the other hand, I can plug any of these for this particular function. I can plug any of these x values in. And this range could also be written this way. I don't know what notation you've been using, but either one's, those are equivalent notations. The domain, I can plug any x value in and get a y value back out, get a range value back in. So for the domain, we're going to say that's all the real numbers. Which is often the case, but I'll show you a couple where that's not. So here we have a domain of all the real numbers. I can plug anything I want into f of x equal to x squared. But what comes out? Only positive numbers. Only positive numbers are what come out. So that's the range. What would be an example of, let me note this while I got this picture up here. You often hear of, when you talk about functions, you hear about vertical line tests, and that's supposed to tell us whether something is a function or not. And it gives us a pictorial example of that. And if we draw vertical lines through this graph, anywhere through this graph, if they only intersect in one point, which you can see that these do, that means we're looking at a function. And that's because that's telling us that each one of these x values, where these vertical lines intersect the x-axis, that then they only correspond with one y value, which we know that that's what a function is supposed to do. So that's why drawing vertical lines through there, that's why that works. Graphically, something that is not a function would be if we turned this parabola on its side. Instead of writing f of x equal to x squared, I'm going to turn it around and say x equal to y squared, just to turn this thing on its side like that. And now you can see if I draw these vertical lines through this function, they often intersect at 2 spots. So for this value of x, say 6 here, you can see that there's a point up here on the graph that has an x value of 6, and then there's a completely different point down here that has an x value of 6. So this is an example of x getting matched, x equals 6 getting matched up to 2 different values of y. So when we draw vertical lines through this graph and they intersect at 2 places, then that tells us that blue curve is not a function. So we don't even have to have a domain and range conversation about that one. All right, so something that does not have a domain that's all the real numbers. The 2 that you see most often are functions that have denominators where the variable is in the denominator, like that. And that's because of what happens when we get a 0 in a denominator. We know that a fraction becomes undefined when you get a 0 in the denominator. So whenever you have x's in the denominator of a function, you have to be careful to what values might make that 0. And you have to exclude those for the domain. So in this case, this one, we would say the domain, all real numbers except see if I can spell. Struggling here. Here we go. Except 0. So in this case, 0 doesn't work because if I plug 0 in here, I get 1 over 0, and that's undefined. We don't like that. And that's why this graph just goes crazy when you get here at x equal to 0. When we get x equal to 0, this thing goes crazy. It goes from this direction, it goes down to negative infinity, and from this direction, it goes up to positive infinity. It doesn't know what to do because at 0, it's undefined. It can't ever equal 0, and even when it gets close, it just goes crazy. So in that case, we have one value that's excluded from the domain. Now, don't get confused by this and think that the only value we ever exclude is 0. The key is what makes the denominator 0. It's not always the number 0 that makes the denominator 0. For example, suppose the denominator of this function was 2x minus 3. So if I plug 0 into this, that is going to be perfectly legit because f of 0 is 1 over 2 times 0 minus 3, which is 1 over negative 3. So I get negative 1/3. So I get a real number back out. That's fine. So 0 is in the domain because when I plug in 0 to this function, I get a number back out. It's matched with negative 1/3 in the range. So that's okay. But this is a fraction, and there are potential problems here. And I can see from my graph, I have it going crazy again. The question is, where is it going crazy? What value do I have to exclude? You have to look at the denominator right there. And the question you have to ask yourself is, where is that 0? What makes 2x minus 3 0? So I do a little scratch work out to the side. So, okay, I'm interested in what makes the denominator 0. So I'm interested in what makes 2x minus 3 0. And now I have a little algebra 1 equation. These are the ones we like to solve. They're easy. And that's 2x equals 3 and x equals 3/2. So when x equals 3/2, this function becomes undefined, meaning if I were to plug 3/2 into this function, I would get 2 times 3/2 minus 3, 1 over 3 minus 3, 1 over 0. Oh no, it's undefined there. So I have to be, and you can see from our graph that where this thing is going crazy is right there at 3/2, which is what? That's 1.5. So I'm going to try to hit that. It's right around here. Oops. That was not much of a line there. If we draw a line down through 1/2, 1.5. This is x equal to 3/2, which is 1.5. We can see that that's where this graph is going crazy, and it's going crazy because this happens. It's undefined at that point. So when you're dealing with a rational function, when you have x's in your denominator and you're trying to figure out what points do I need to exclude from the domain, think, well, what values of x make it undefined? That's easy enough to find. Take the denominator, set it equal to 0, and solve. And then those are the values that you have to remove. So in this case, the domain, all real numbers except this time 1.5 or 3/2. The other one you run into fairly often when dealing with functions is when you're dealing with square roots. And actually all even number roots, but let's just look at square roots. That's by far the most common. We have a function that looks like f of x equal to where's my square root here? Let's see. Square root of x. And this thing, I guess, just to be, I need to put my little 2 up there. That means square root. I get something that looks like that. Now you could see it looks kind of like a half of a parabola on its side. That one is actually exactly what it is. But what you notice here is that we no longer have any x values that have corresponding y values over here on the negative x-axis. This sucker, instead of going off in both directions to infinity like you see most often, this one just dies right here at 0. And that's because of what we know about square roots and negative numbers. That when we take the square root of a negative number, we get an imaginary number, which takes us out of the realm of the real numbers into a whole different set of numbers. And when we're dealing with functions, we're talking about things that match real numbers up with real numbers, not real numbers matched with imaginary numbers. So what you have to be concerned about when dealing with square roots is what makes it negative, what makes it less than 0 underneath that radical, underneath that square root. And those are the values that we have to exclude. From the domain. Let's see. So all right, let's look at an example. Now this one is fairly obvious because it's a pretty simple function, and we can see whenever x goes negative that we get the square root of a negative number, and that makes gives us an imaginary number back out, and that's not what we want. So it's pretty obvious with this one that the domain are all the x values greater than or equal to 0. But what if it's not so obvious? What if we have a function that looks like, let me just recycle this one, under a radical 2x plus 3. It's not just x greater than or equal to 0 anymore. Not as obvious. So how do we solve that? Well, we asked the same question that we asked before. What makes what is under the radical negative? So what makes 2x plus 3 negative? So what do I want? I want that to always be greater than 0. So the domain is everything that makes that greater than, well, actually greater than or equal to 0, right? It can be 0. So anything that makes 2x plus 3 greater than or equal to 0, well, then I can take the square root of it and I get a value here. It'll still be on this curve, but you can see this curve terminates right there as well. So the question is, what values what x's satisfy this inequality here? So we can solve this inequality like you are used to. Let's see, we'll subtract 3 from both sides, and we get that. And we'll divide by 2, and we get this. So this tells us that our domain is all values of x that are greater than or equal to 3/2. Why? Because when I plug any number starting at -3/2, which happens to be right there, coincidentally, not coincidentally, and up, I get positive numbers under this radical. So it doesn't matter that the x itself is negative. It's what makes it negative under the radical. So when you have one of these to do, when you have the ones with denominators, x is the denominator, set the denominator equal to 0, solve, exclude that value from the domain. When you have radicals involved, like square roots specifically, the odd number radicals like cube roots and stuff, they're different. But anyway, when we have square roots involved, take what's underneath the radical, this 2x plus 3 in this case, say, okay, that has to be greater than or equal to 0, or I'm going to get in trouble. Then solve that little inequality, and that gives you the domain for a function like this. So there's a little brief overview of functions and their domain and their range.